Okay, good morning, guys. It's Friday now when you're watching this, hopefully. And we're just finishing up with our last day here on Unit 2, which is all about Chapters 2 and 3 in the textbook. So we're finishing up just some loose ends, really, now with connections between entropy, the microscopic models, and thermodynamics. So we're going to talk about heat capacity, even though we're very close to heat capacity already, talking about heat. But we're going to explicitly give some relationships for heat capacity. And then we are going to talk about the last derivative that we can take of the entropy called the chemical potential. And then we are finally going to introduce the last law of classical thermodynamics, justify it from the microscopic viewpoint, and that is the third law. Just so you know, the third law is not really very important for what we're doing going forward, but it is something worth knowing what it is. So we'll have a brief talk about that. Okay, so let's begin on the paper with the linkages between the microscopic model, entropy, and heat capacity. Okay, so our original definition of heat capacity in Chapter 1 was that during an isobaric or an isochoric process, we could relate the amount of heat added to the temperature change. And we know that this isn't valid for like an isothermal or an adiabatic situation, but it is valid for situations of constant pressure and constant volume. So we can relate this heat now to entropy flow into the object by our relationship from last class. Now these two equations we can use to eliminate the explicit dependence on heat here. And we get this interesting looking equation which relates the change in entropy to the change in temperature directly. So as we always expected, adding entropy to an object increases its temperature, and this here we see a direct relationship. The way we're going to use this though is assuming we have known the formula for the entropy, we can use that to get the heat capacity directly. So I'll just sort of solve this for the heat capacity here, dividing both sides by dt, and then realizing when I have the ratio of two differentials that is a derivative. So in general, we will expect that the heat capacity of a system can be found directly from the entropy if the entropy is expressed in terms of temperature. We just take this derivative. We do have to multiply by T, and then that gives us the heat capacity. Okay, so of course there are, as we know, two different versions of the heat capacity, depending on whether the system is held at constant volume or held at constant pressure. And all that's going to change here is which variables we need to put the entropy in terms of. We don't have to talk about work or the first law at all to use these two relationships. We just have to make sure our formula for entropy involves only temperature and volume here, or to get this heat capacity, the formula for entropy only depends on temperature and pressure. So let's kind of see how that actually plays out as these two derivatives in a model system. So I'm going to write out now as an example the entropy of the ideal monoatomic gas. Okay, so we have that in our book from earlier. And now we're going to see if we can use these two versions of heat capacity to get it directly from this. Well, the bad news is that starting from this, we cannot get these in one step, because remember, when we write a derivative like this, it requires us to express the numerator function in terms of the two denominator variables, one of them varying, the other held constant. So we do need to know something about temperature, volume, and pressure in the system before we can change this formula around. So luckily we did that last time. We found out that the internal energy is related to temperature by 3/2 nkt. The pressure is related to temperature and volume through the ideal gas equation. And then the idea of these is that we use these two equations of state that we got by derivatives to rewrite the entropy in terms of T and V or T and P. So let's do that now. First, let's do the heat capacity at constant volume. Since that one has already got the V in there for us, we won't have to mess with that. We just have to get rid of this U in favor of temperature. So I'll be plugging in 3/2 nkt into the U. And that will give me a, let's see, the 3's will cancel, the n's will cancel. The U will have a kt divided by 2 left over. The divided by 2 can turn this 4 down into a 2. So I'll have 2 pi m kt over h squared. Everything else on this denominator was canceled here, the 3n and the 3n. All right, that is still all to the 3/2 power, and we still have the added 5/2 at the end. All right, now this entropy formula is in terms of temperature and volume, so we can take this derivative. First, let's just do the derivative by itself. Okay, the nk in front is a constant. The logarithm, we treat v as a constant, we treat n as a constant. All these other quantities here are constants. We're only interested in the t to the 3/2 power. So that derivative is going to become 3/2 times the derivative of natural log of t by itself, so 1 over t. This 5/2 has no t in it, so that is it. So 3/2 nk times 1 over t. All right, now to actually get the heat capacity, we just need to multiply that derivative by t. So I'll rewrite the rule here so I don't forget it. And so just multiplying this by t gives me 3/2 nk. So that is the heat capacity at constant volume directly from the entropy formula. In the small amount remaining here, let's just see how this works out for pressure. We'll get a little instruction on what this means again to have a P down here. It means we need to write the entropy in terms of pressure and temperature, not using energy and not using volume. So first let's look at what happens to the V over N. I'll be able to eliminate the V's using the ideal gas law basically. V divided by N would amount to KT divided by P. So here for the V over N, to prepare for this derivative, I will switch that for KT over P. And then I'll do the same thing for the internal energy that I did in the previous heat capacity. This will change to 2 pi mkt over h squared to the 3/2. All right, so finally let's do this heat capacity at constant pressure all in one go. I've got the entropy expressed in terms of pressure and temperature. But notice what that did is it put the pressure in the denominator. That's going to be held constant, so it's not really important, but it's there now. And it gave me another factor of temperature inside of the logarithm. So if I look at the total presences of temperature in here, I've got T here and the T to the 3/2 that came from U. So the argument of this natural log is dependent on T to the 5/2 power, 3/2 plus 1. So when I do my derivative here, I'm going to have the nk, the 5/2, and the 1 over T. So you see how this differs from this because we put this in terms of P instead of in terms of V, and that changed the places that the temperatures were. Okay, so when we simplify this, we'll just get back to 5/2 nk, which we understood in the past was the heat capacity of that gas at constant pressure. Okay, so I think that's a neat way to do it. You can apply this to any system where you know the entropy formula. If it's not clear whether there's a volume or pressure involved, you can always just take ds dt and multiply it by T to get the heat capacity of some type, right? Okay, so that basically covers this example of heat capacity. There's one more that I would like to do that is interesting. And this is a prediction that we have not made yet. So we'll see what happens. We're going to look at the Einstein solid. And we're going to try to predict its heat capacity. You know, as we did these calorimetry problems all through chapter 1, we were often told, say, the heat capacity of such and such metal, copper, steel, or whatnot, is measured to be a certain value, right? So our only recourse for those problems was to look up the heat capacity, or the specific heat, actually, of that material in a table. But the Einstein model of the solid, you know, it's supposed to be a model for the solid, for solids. So let's see how good of a job it does at predicting the heat capacity of that solid matter. So I'm going to save a little time here by not beginning at the very beginning of the model again. All right, I am going to well, I'll write this down, even though I'm not really going to use it. There's no harm in seeing an equation again. That's the formula for entropy in terms of quanta, Q. Quanta are related to the internal energy, U. And when we did the derivative to get the temperature, we found out that we could write the number of quanta in terms of temperature like this. You know, you do this derivative, you have to boot up a bunch of simplifications, but eventually you end up with this. And that means that the energy of the Einstein solid internally is just Q times epsilon, the energy unit. Okay. So from this we can predict the heat capacity. There's not really any reference to pressure or volume here. So we'll just do this derivative as it is. It turns out it will technically be at constant volume, but that's okay for a solid. But we're going to do a little bit of a, we're going to make an approximation here to make our lives easier. Of course, we could do this derivative exactly. It's tedious, but it's not impossible. There are no special tricks that are needed. We would need to take this formula, all right, or this formula, right, use it to eliminate Q in the formula for entropy, and then we would have entropy as a function of temperature and number of oscillators, and we would take the derivative of S with respect to T. That would give us the heat capacity. Right? I believe that is referenced at some point in the textbook, and it's quite a long calculation. It doesn't really actually give you a very useful prediction because most solids exist in a state where there are many quanta per oscillator. It's called the high temperature limit, and that's what we are going to make our prediction for. So in the high temperature limit, what's our comparison? We will say that the temperature times Boltzmann's constant, this is sort of the thermal energy scale, is much greater than the energy unit of an oscillator. So that's going to mean that down here, epsilon divided by kT is extremely small. So E over kT is much, much less than 1. That's our comparison there. And then if we ever, in any branch of physics, have the exponential of something which is extremely small, that is approximately equal to 1, and the next best correction is 1 plus the exponent. Okay, so we'll be using that. And then, of course, when this appears in the denominator, the 1 plus epsilon over kT has this 1 subtracted off. So that means Q will be approximately equal to N divided by epsilon over kT, or where we start our high temperature limit on the next page, Q is approximately equal to N kT over epsilon. All right, so this is a high temperature limit result for the Einstein solid. It's easy to understand. If you have nkt is like your energy, you just divide by the size of the energy unit, you get the number of units. For our internal energy then, simply comes out equal to nkt. N is the number of oscillators, Boltzmann's constant, and temperature. So now let's go after this heat capacity. Sorry, this didn't go anywhere. So we're picking it up back over here, actually. And now in this high temperature limit, rather than doing that whole tedious plugging in and derivative that I alluded to back here, we are going to use a mathematical assistance here. We are going to do ds du and du dt as a chain rule with u as the intermediate variable for that derivative. So the ds du is defined as 1 over t, and so the du dt is the only one we really need to do. And here is u as a function of t, so this heat capacity is just equal to nk for the Einstein solid, where n is the number of oscillators. Now there is some question about what is the number of oscillators and how is it related to the number of atoms. But when your crystal is a simple structure, if it's just got one atom at each lattice site and the atoms are in a regular crystal structure, then there will basically be 3 directions that each atom can oscillate. So it will be 3 oscillators per atom. So when we put this in terms of the number of atoms, which I'll write as n sub a, number of atoms, the heat capacity of that Einstein solid is 3 times the number of atoms times Boltzmann's constant. Now we can make one more very simple change to this, just a transmutation from atoms to moles that makes this much more easy to apply in the large scale. We have a product number of atoms times Boltzmann's constant, so that is equivalent to the number of moles times the ideal gas constant. And that gives us a very clean result. If we divide this heat capacity by the number of moles, we get something that's called the molar specific heat, and that is simply 3 times the ideal gas constant. So that's a surprisingly general prediction that is actually followed very closely by mostly every solid that has a simple crystal lattice structure. So basically all metals, if you search their specific heat in a table and their molar mass, all right, if you put those two together, you will find that their specific heat per mole is basically 3R. So it's basically 8.31 for R times 3 is about 25. Right? So the molar specific heat of almost every metal is about 25 joules per mole per Kelvin. That observation, that conclusion, it was known long before the Einstein solid was invented, but that is known as the law of Dulong and Petit. And so it gives us a great prediction for mostly any solid of a constant heat capacity, a constant specific heat, which is equal to the same thing in molar terms for every different metal. Okay, so the next connection we're going to make is to the last derivative we can take of the entropy. And that is the derivative with respect to the number of particles in the system. This is related, I'll just tell you, to a quantity called the chemical potential, which we will symbolize throughout the course as a lowercase mu. And the definition is that ds dn at constant energy and volume is equated to the opposite of the chemical potential divided by the temperature. So what is the point of defining it in this way, and what is the chemical potential? How does it behave? Well, to understand the chemical potential, we need to think about ways that the system change its particle number, right? That's what this derivative is all about. Can the system increase its entropy, approach equilibrium, by changing its particle number? Now, if it's just an ideal gas or an Einstein solid, it can't just create new particles out of nothing, right? Conservation of mass, conservation of energy, make that an inaccessible option, right? So you can't maximize entropy just by creating particles out of thin air. They have to come from somewhere else, or they have to be created by something else breaking down or changing. So we have basically 3 ways that the number of particles in a system can change. First one is particles just come in from the outside. So you've got your ideal gas in a box, but it's not closed off, and things can leak in or out. Do they want to leak in, or do they want to leak out? That's going to be determined by really the chemical potential. The other situation is where we have our system actually divided into two portions. And we may be able to increase the entropy by having some particles move from one portion to another. So this process is called diffusion. And it's a trading of particles between two different parts of the system. So this is from outside. So there's an external source of particles coming in. The second one here is diffusion. The third option is to have our particles be created within the system at the expense of other particles being destroyed. And this is a process where we have some particles, they break up into other pieces, or they combine from smaller parts. Essentially, these are chemical reactions. Okay, so the chemical potential will tell you whether it is favorable in terms of entropy for a molecule to break up into two pieces, or alternatively for two smaller molecules to combine into one. Right? We know examples of this, right? The normal state of most gases is diatomic. But there are monoatomic gases as well. Why are some diatomic and why are some monoatomic? Well, the diatomic ones have a lower chemical potential than their monoatomic option. So the chemical potential is what controls really the seeking of diffusive or chemical equilibrium. So it's not really appropriate to go into too much detail about the chemical potential at this time, because we need to treat it appropriately, give it its due, spend the time talking about chemical reactions themselves and how they're allowed to happen, what are the reactions, and how do we get the chemical potential of each molecule. So we'll come back to that much later, but I did want to give you that awareness that this is what the chemical potential is all about. All right, so one way to think of the chemical potential just conceptually is to look at this equation, all right? Nature is always going to try to maximize the entropy, all right? So if a system has an entropy that increases when particles are added, that system is going to want to add particles. So that means this derivative, when it's positive, the system wants to gain particles, okay? So if this derivative is positive on this side, then the chemical potential is going to be negative. So this is a system where ds dn at this point is big. If a system, for some reason, gains a lot of entropy by losing particles, that is going to give this a negative value, right? dn goes down while ds goes up. That is going to give that system a negative derivative here and a positive chemical potential. So ds dn would be would be negative down here, and that means the chemical potential would be positive. So you can really get a good conceptual intuition about chemical potential by thinking about it like any other kind of potential. For example, a gravitational potential. Chemical potentials that are negative are analogous to holes, deep holes in the ground, where some particles would naturally try to fall down into those. Chemical potentials that are very high are like high hills on the terrain. Particles would naturally not want to be stable up at the top of the hill. They will tend to roll down off of that to lower their chemical potential. right? So what we'll find when we get to this is that chemical potential is a way to determine which molecules are favorable and which are not. So a high chemical potential, if it has the option, if it's allowed by conservation of energy, a mass, an atom type, a molecule high chemical potential will break down in favor of creating products with low chemical potential. Right, let's see an option of this with the chemical potential for our favorite old system, the ideal gas. I'll take time to write this out one last time. And here, let's first do the derivative that's required. The derivative of this with respect to n, luckily with constant volume and constant energy, so the way it already is. Okay, so this derivative is a little bit more difficult than the previous one, so I'm going to do it for you because n appears more than one place now, right? V is just here, u is just here, but n is 3 places. So first, we're going to have this n at the front. We'll have like a chain rule between this and this. Product rule between this term and this term. So first, we'll just have k from differentiating this. And I'll quickly rewrite the entire inside. Okay, and then we'll have the nk, the first term, times the derivative of the inside. The derivative here, we've got a constant that goes to 0. Everything else here is constant except the n. The n is to the -1 power here and to the -3/2 power here. So the total power of n inside the logarithm is -5/2. So for this, we're going to get -5/2 1 over n. All right, just to show that for us. We use this exponent rule for logs, and then we get this for the derivative very simply. All right, now check out what's going to happen with that product rule term here and this 5/2 we've been carrying around forever without saying anything about it. This n is going to cancel this. The k is on both terms. This 5/2 is positive, this one is negative. So this term here that we've been carrying around actually serves to kind of cancel out with this when we go for the chemical potential. So this derivative ends up with being Boltzmann's constant times just the logarithm. And that's it. So when we go to calculate the chemical potential, we just have to multiply that by -T, and then we've got it for this monoatomic ideal gas. All right, so that's the chemical potential in terms of volume, particle number, and total internal energy. Of course, you can plug in for all these things and get a value for mu. It's not particularly illuminating on its own, just gives you some energy amount. But it's also not very useful to have this in terms of U, V, and N, in terms of predicting kind of how gases behave in reactions. So let's just change this a little bit to what's called a standardized form. The volume and particle number, we can change that to kT over P, like we did in the ideal gas equation previously. The internal energy, we can change that to 3/2 nKT, like we also did previously. So this formula here is going to depend on the temperature to the 5/2 power. And we'll standardize that by dividing it by a reference temperature T0. Now T0 is actually 298 Kelvin. Then we're going to have a pressure in the denominator. So P in the denominator of this, V over N. And we'll standardize that by multiplying on the numerator by a reference pressure, P0. You might expect this to be atmospheric pressure, but it's actually, due to the chemists, this is standardized at 1 bar, 100,000 pascals. Okay, and this internal of the logarithm now is unitless. So kT gives the units of energy, and since we've kind of mucked up our 4 pi, our m, our h bar squared in favor of these reference values, that gives us basically just a constant offset to the chemical potential. From all, you can think of this as all these constants getting shuffled outside of the logarithm and collected by themselves along with the T0 and the P0. And that's all just put together into a single value of mu energy called mu0. So this is, if you go to do chemical potentials for a ideal gas, you will end up starting from this formula, looking up the power of temperature here. This is related to the degrees of freedom. And you would look up the mu0 value for that specific gas in a table. Okay, so that's how the chemical potential works for the ideal gas in terms of the formulas. And you can tell from here a bit about its behavior. If the pressure of the gas goes up, this fraction goes down, the logarithm as a whole goes down, there's a minus sign in front, so the chemical potential goes up. So if the pressure goes up, the chemical potential goes up, and that pressurized gas is less favorable to have particles in it than some lower pressure region nearby. Okay, so that's how we expect chemical potential to behave, shuffling around particles to regions where chemical potential is lower. All right. Okay, so our last thing to tie up today is unrelated to the first two. It is the third law of thermodynamics. And as I mentioned in the introduction, this law is not crucially important for most of the rest of what we do, but it is good to know that it exists and know a little bit of what it means. So again, as it's a law of thermodynamics, we don't need to justify it within thermodynamics itself. We can take it as a starting point. But coming up from the microscopic models, we can justify it quite well with our understanding of multiplicity, entropy, and energy in the microscopic models. So let's start from that perspective. Okay. In a microscopic model, as the energy approaches its minimum possible value, or the ground state energy, or we could also call this our 0 point of energy, we are going to have less and less options for distributing that energy, right? Whether it's the velocities that are available to the gas particles, whether it's the number of quanta or the number of spins that are flipped up versus down. As the energy goes away, there are less ways to distribute it. If we go down to the minimum possible energy, there will only be essentially one way to distribute it. Okay, so our multiplicity goes down to 1. This would be like the two-state system with all entities flipped down. There's only one way to get them all down, so there's one multiplicity. Or the Einstein solid with no quanta. If there's no quanta anywhere, all of the oscillators just have a 0, and there's only one way there's only one unique way, they're all 0, right? So when that multiplicity is equal to 1, then the entropy is equal to 0, because entropy is proportional to the natural log. Okay, so as U approaches its minimum, the entropy of the system approaches 0. All right, and that is one way of stating the third law of thermodynamics. Now, there's a little bit more that we could say about this if we invoke the concept of temperature. Okay, so as we know, temperature is related to the entropy and energy of a system. If entropy is going to 0 and energy here is going to some 0 value as well, this derivative is, it's actually not totally determined just by saying these both go to 0, right? But we're going to do a sort of a derivation here that shows how these things need to behave. And it will be based off of this. Assume the entropy, the entropy approaches 0. So let's assume that the entropy approaches 0 as some power of the temperature, x, where x just needs to be a positive power. If x was a negative power, the entropy would diverge at 0 temperature. But with a positive power there, it's going to go to 0 in some way. All right? So if we do that, let's first see what happens to the energy. So remember, du is T ds. And ds now is going to be C. This is an undetermined constant, okay? It's not the heat capacity. Maybe I'll just make it A to make that clear. So that's just some arbitrary undetermined constant for a particular system that multiplies the temperature to the x power to give the entropy. Okay, so if I do ds, I'm going to get A x t to the x minus 1 dt. And that I can simplify to ax, the t's multiply to get rid of the minus 1. So ax, a times x times t to the x times dt. All right, so du is a times x times t to the x dt, like that. All right, so this is just u versus t now. I can integrate this. So u would have to be some constant of integration, a times x. I'm integrating, so I divide by the, I raise the power of x, I raise the power of t to the x plus 1, and I divide by x plus 1. So this is the function energy of temperature. And so we see the internal energy must approach its minimum as t to the x plus 1 power. All right. So this is not a necessarily universal result. It's based on our assumption here that the entropy goes as t to the x. But if we combine those two things together, all right, let's do this. So S is a to the t, a times t to the x, and t is u minus u0 divided by kind of just some junk constants, right? To the 1 over x plus 1, right? We subtract u0, divide by this stuff, take it to the 1 over x plus 1 power on both sides, and then the x here comes into the numerator, so like that. All right? So basically then S is equal to just some different constant times u minus u0 to the x over x plus 1. Now that's an interesting power dependence because x is greater than 0, so this is positive, right? And clearly, clearly x plus 1 is greater than x, right? Because, you know, x is positive, so x plus 1 is greater than x. So that means x over x plus 1 is a smaller divided by a bigger. So it's less than 1. So this plot of entropy, which bottoms out at 0, versus energy, which bottoms out at u0, always behaves as if it, no matter what the power x is, no matter what the power x is in our assumption up here, this plot of entropy versus energy always goes as u to some fractional power. The power of u is between 0 and 1. So that's always going to look like some type of root. It's going to be concave down. It's going to be sloping up. Like, for example, S might be equal to u minus u0 to the, say, 2/3 power, something like that, right? So if we look at this power, u minus u0 to the 2/3, right? This is always going to give us sort of a slope here at the origin which is infinite, right? Any sort of function like this with a fractional power, it's going to give us a slope here which is infinite. Basically, we're going to be drawing, if we drew in this direction, we'd be making some sort of parabola here or cubic here like this. Okay. All right, so what that means right here is ds du approaches infinity. And so t approaches 1 over infinity, t approaches 0. So it's all consistent, all right? As the slope here gets extremely large, the temperature gets extremely small. So this is what all systems have to look like as their temperature approaches 0 on an absolute scale. Their entropy must go to 0 with temperature. Their internal energy must go to 0, go to u0 with some other power of temperature as temperature goes to 0. So the last version of the third law we can get is to express it in terms of heat capacity. So C is T times ds dt. Oh, so it's a little bit connected to what we did at the start. But under our assumption that S equals A times T to the X, then this heat capacity will be C times A times X T to the X minus 1. That's the derivative. And then so AX times T to the X. So the heat capacity must approach 0 as well at 0 temperature. So that's actually an interesting result. the heat capacity actually approaches zero with the same dependence as the entropy itself. Same dependence on temperature. So we might have expected at some point to just have this heat capacity be like 1 joule per Kelvin all the time, and then we can just keep taking out joules and keep lowering the temperature. Doesn't matter what temperature we're at. If the heat capacity is still 1, we take out 1 joule, we lower the temperature by 1 Kelvin, right? That's how heat capacity works. But what the third law says is that the heat capacity cannot be constant down to 0 temperature. The heat capacity must also approach 0. So as I get objects, as I start to get them really cold, their heat capacity starts going down and becoming really small. And what that means is when I have a very small heat capacity, right, very small amounts of heat can produce really big changes in temperature. Right? At a very low temperature, where the heat capacity has become extremely small, any tiny amount of heat added to that system is going to increase the temperature by a large amount. So the third law also says that it is incredibly difficult, actually impossible, to make a system reach 0 temperature, because by the time it gets very close, its heat capacity has become so small that it becomes harder and harder to extract heat from that object to lower its temperature more. Right? Small heat capacity makes it hard to get heat to come out. Any little leakage of heat in will just boost that temperature way up really quickly. Okay? So that's the final way that the third law is stated, is to say it's impossible to reach, it's impossible to actually reach 0 temperature, right? Because the heat capacity of the object becomes also extremely, also approaches 0 as it goes down. Okay, so that will conclude the material for Unit 2. Summarize this video, we had the definition of heat capacity then in terms of entropy directly. We discussed that for the ideal gas and for the Einstein solid, making a prediction that matched the law of Dulong and Petit. We then looked at the chemical potential, the derivative of entropy with respect to particle number, and kind of became aware of it, introduced it, but didn't really do very much with it. Just got a conceptual feeling for what it is and why it exists. And then finally, we just briefly covered the third law of thermodynamics, which guarantees that absolute 0 is a real thing and it really is 0 temperature. The entropy goes to 0 at that temperature. The heat capacity of any system goes to 0 at that temperature. And so it can never really be reached exactly. We can only get arbitrarily close, but not actually ever get to 0 temperature. Okay, guys, thanks for watching this video. Feel free to email me if you have any questions, and I will see you after break.